Welcome to Soil Mechanics Fundamentals, Part 2. In Part 1, we discussed the introduction to soil mechanics, origin and types of soils, and the concept of the three-phase system. In this session, we will continue with phase relationships, volumetric ratios, weight ratios, unit weights, specific gravity, Atterberg limits, soil classification, and important numerical concepts used in geotechnical engineering. These topics are essential for understanding soil behavior and solving engineering problems related to foundations and earth structures. Now, let us begin with volumetric ratios. I am Mr. S. Vinoth, Assistant Professor in the Department of Civil Engineering at KPRIET Institute of Engineering and Technology. I completed my Bachelor of Engineering in Civil Engineering from KPRIET Institute of Engineering and Technology and pursued my Master of Engineering in Structural Engineering at Sri Shakti Institute of Engineering and Technology. I also worked as a technical assistant in the town planning section at Singanallur Corporation Office, Coimbatore, where I gained practical exposure in planning and infrastructure-related activities. My areas of interest include structural engineering, infrastructure engineering and management, and earth system science and engineering. Through this course, I aim to explain the concepts of soil mechanics in a simple, practical, and application-oriented manner. Let us continue with the fundamentals of soil mechanics. In Part 1, we already discussed the origin and formation of soils, and the three-phase system of soil. In this session, we will continue with the remaining important topics from Unit I. The topics covered in this part include phase relationships, index properties, Atterberg limits, soil classification using IS and USCS systems, and important numerical problems related to soil properties and phase relationships. These concepts are very important for understanding soil behavior and solving geotechnical engineering problems. Now, let us begin with phase relationships in soil. Volumetric ratios describe the relationship between different volumes present in a soil mass. The important volumetric ratios are void ratio, porosity, and degree of saturation. Void ratio is defined as the ratio of the volume of voids to the volume of solids. Porosity is defined as the ratio of the volume of voids to the total volume of soil. Degree of saturation represents the percentage of void spaces filled with water. These parameters help engineers understand soil compactness, density, and moisture condition. They are widely used in phase relationship calculations and numerical problems in soil mechanics. Weight ratios describe the relationship between the weights of soil components. The most important weight ratio is water content. Water content is defined as the ratio of the weight of water to the weight of soil solids, usually expressed as a percentage. Water content greatly influences soil strength, compressibility, and permeability. An increase in water content generally reduces soil strength and increases compressibility. Therefore, determining water content is very important in geotechnical engineering practice. Unit weight is defined as the weight of soil per unit volume. Different unit weights are used depending on the moisture condition of soil. Dry unit weight represents the weight of solids divided by the total volume of soil. Bulk or moist unit weight includes the weight of both solids and water. These unit weights are important in calculating vertical stresses, bearing capacity, and earth pressure in soil engineering problems. In fully saturated soil, all void spaces are filled with water. The saturated unit weight represents the unit weight of soil under completely saturated conditions. Submerged unit weight represents the effective unit weight of soil below the groundwater table. It is obtained by subtracting the unit weight of water from the saturated unit weight. These unit weights are widely used in seepage analysis, earth pressure calculations, and underwater foundation problems. Specific gravity of soil solids is defined as the ratio of the weight of soil solids to the weight of an equal volume of water at 4 degrees Celsius. Specific gravity indicates the mineral composition of soil particles. It is an important parameter in phase relationship calculations. Specific gravity is used in determining void ratio, degree of saturation, and unit weights. For most inorganic soils, the specific gravity value generally ranges between 2.65 and 2.80. Different soil types have different ranges of specific gravity values. Sands usually have values around 2.65. Clays generally have slightly higher values. Organic soils have lower specific gravity values because of the presence of organic matter. Specific gravity helps engineers identify soil type and understand soil composition. These values are also useful in solving numerical problems involving phase relationships. All weight, volume relationships in soil mechanics are derived from a few basic definitions. These include void ratio, porosity, degree of saturation, water content, unit weight, and specific gravity. Understanding these relationships is very important because they simplify three-phase numerical problems. Most phase relationship equations used in soil mechanics are obtained from these basic definitions. This slide explains the relationship between void ratio and porosity. Void ratio is defined as the ratio of void volume to solid volume, while porosity is defined as the ratio of void volume to total volume. Since total volume consists of both solid volume and void volume, these two parameters are mathematically related. The derived equations help engineers convert void ratio into porosity and vice versa. These relationships are frequently used in seepage, compaction, and permeability problems. This is one of the most important relationships in soil mechanics. It connects degree of saturation, void ratio, water content, and specific gravity. If any three parameters are known, the fourth parameter can be easily calculated. This relationship is very useful in solving three-phase numerical problems and reducing lengthy calculations. This slide presents the general equation for calculating the bulk or moist unit weight of soil. The equation incorporates void ratio, degree of saturation, and specific gravity. By adjusting the value of degree of saturation, the same equation can be used to determine unit weights for dry, saturated, and submerged soils. The derivation starts from the basic definition of unit weight as total weight divided by total volume. The total weight is expressed as the sum of weights of solids and water, and the total volume as the sum of volumes of solids and voids. By substituting appropriate expressions and simplifying using definitions of void ratio and degree of saturation, the final equation equals _plus, slash, 1 plus, _ is obtained. This slide highlights the final form of the unit weight equation. It clearly shows how soil structure, moisture condition, and material properties influence unit weight. This equation is widely used in stress analysis, bearing capacity calculations, and earth pressure problems. This slide summarizes the important relationships used in soil mechanics. These equations connect weight parameters and volume parameters of soil. Understanding these relationships is essential for solving numerical problems quickly and accurately. These formulas are commonly used in university examinations, competitive exams, and practical engineering calculations. This slide presents the general equation for calculating the bulk or moist unit weight of soil. The equation incorporates void ratio, degree of saturation, and specific gravity. By adjusting the value of degree of saturation, the same equation can be used to determine unit weights for dry, saturated, and submerged soils. The derivation starts from the basic definition of unit weight as total weight divided by total volume. The total weight is expressed as the sum of weights of solids and water, and the total volume as the sum of volumes of solids and voids. By substituting appropriate expressions and simplifying using definitions of void ratio and degree of saturation, the final equation equals _plus, slash, 1 plus, _ is obtained. This slide highlights the final form of the unit weight equation. It clearly shows how soil structure, moisture condition, and material properties influence unit weight. This equation is widely used in stress analysis, bearing capacity calculations, and earth pressure problems. This slide reiterates the conversion formula between porosity and void ratio. It emphasizes that void ratio is more commonly used in soil mechanics calculations, while porosity is often required in seepage and flow problems. This slide introduces the relationship between dry unit weight and bulk unit weight. The equation shows that dry unit weight can be obtained by dividing bulk unit weight by 1 plus water content. Dry unit weight is particularly important in compaction and foundation engineering problems. Thank you for watching Soil Mechanics Fundamentals, Part 2. In this session, we discussed important phase relationships in soil mechanics, including volumetric ratios, weight ratios, unit weights, specific gravity, and relationships among different soil parameters. We also studied important equations connecting void ratio, porosity, degree of saturation, water content, and unit weight. These concepts form the foundation for solving numerical problems in soil mechanics and geotechnical engineering. In Part 3, we will continue with Atterberg limits, soil classification using IS and USCS systems, and important numerical problem-solving concepts. Thank you once again. Let us continue our learning journey in Part 3.